Section 12 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larissa Jaworski, Brisbane, Australia, March 2007. Familiar Letters on Chemistry by Justice Liebig. Letter 12. My dear Sir, having now occupied several letters with the attempt to unravel, by means of chemistry, some of the most curious functions of the animal body, and, as I hope, made clear to you the distinctions between the two kinds of constituent elements in food and the purposes they severally subserve in sustaining life, let me now direct your attention to a scarcely less interesting and equally important subject: the means of obtaining from a given surface of the earth the largest amount of produce adapted to the food of man and animals. Agriculture is both a science and an art. The knowledge of all the conditions of life of vegetables, the origin of their elements, and the sources of their nourishment, forms its scientific basis. From this knowledge we derive certain rules for the exercise of art, the principles upon which the mechanical operations of farming depend. The usefulness or necessity of these for preparing the soil to support the growth of plants and for removing every obnoxious influence. No experience, drawn from the exercise of the art, can be opposed to true scientific principles, because the latter should include all the results of practical operations, and are in some instances solely derived therefrom. Theory must correspond with experience, because it is nothing more than the reduction of a series of phenomena to their last causes. A field in which we cultivate the same plant for several successive years becomes barren for that plant in a period varying with the nature of the soil. In one field it will be in 3, in another in 7, in a third in 20, in a fourth in 100 years. One field bears wheat and no peas, another beans or turnips but no tobacco. A third gives a plentiful crop of turnips, but will not bear clover. What is the reason that a field loses its fertility for one plant, the same which at first flourished there? What is the reason one kind of plant succeeds in a field where another fails? These questions belong to science. What means are necessary to preserve a field its fertility for one and the same plant? What to render one field fertile for 2 or 3 for all plants? These last questions are put by art, but they cannot be answered by art. If a farmer, without the guidance of just scientific principles, is trying experiments to render a field fertile for a plant which it otherwise will not bear, his prospect of success is very small. Thousands of farmers try such experiments in various directions, the result of which is a mass of practical experience forming a method of cultivation which accomplishes the desired end for certain places. But the same method frequently does not succeed. It indeed ceases to be applicable to a second or third place in the immediate neighbourhood. How large a capital and how much power are wasted in these experiments! Very different and far more secure is the path indicated by science. It exposes us to no danger of failing, but on the contrary it furnishes us with every guarantee of success. If the cause of failure, of barrenness in the soil for 1 or 2 plants, has been discovered, means to remedy it may be found. The most exact observations prove that the method of cultivation must vary with the geognostical condition of the subsoil. In basalt, greywacke, porphyry, sandstone, limestone, etc., are certain elements indispensable to the growth of plants, and in the presence of which renders them fertile. This fully explains the difference in the necessary methods of culture for different places, since it's obvious that the essential elements of the soil must vary with the varieties of composition of the rocks, from the disintegration of which they originated. Wheat, clover, and turnips, for example, each require certain elements from the soil. They will not flourish where the appropriate elements are absent. Science teaches us what elements are essential to every species of plants by an analysis of their ashes. If therefore a soil is found wanting of any of those elements, we discover it at once the cause of its barrenness, and its removal may now be readily accomplished. The empiric attributes all his success to the mechanical operations of agriculture. He experiences and recognises their value without inquiring what are the causes of their utility, their mode of action, and yet this scientific knowledge is of the highest importance for regulating the application of power and the expenditure of capital, for ensuring its economic expenditure and the prevention of waste. Can it be imagined that the mere passing of the ploughshare or the harrow through the soil, the mere contact of the iron, can impart fertility miraculously? Nobody, perhaps, seriously entertains such an opinion. Nevertheless, the modus operandi of these mechanical operations is by no means generally understood. The fact is quite certain that careful ploughing exerts the most favourable influence. The surface is thus mechanically divided, changed, increased, and renovated, but the ploughing is only auxiliary to the end sought. In the effects of time, in what in agriculture are technically called fallows, the repose of the fields, we recognise by science certain chemical actions which are continually exercised by the elements of the atmosphere upon the whole surface of our globe. By the action of its oxygen and its carbonic acid, aided by water, rain, changes of temperature, etc., certain elementary constituents of rocks, or of their ruins which forms the soil capable of cultivation, are rendered soluble in water and consequently become separable from all their insoluble parts. These chemical actions poetically denominates the tooth of time, destroy all the works of man and gradually reduce the hardest rocks to the condition of dust. By their influence the necessary elements of the soil become fitted for assimilation by plants, and it's precisely the end which is obtained by the mechanical operations of farming. They accelerate the decomposition of the soil in order to provide a new generation of plants with the necessary elements in a condition favourable to their assimilation. It is obvious that the rapidity of the decomposition of a solid body must increase with the extension of its surface. The more points of contact we offer in a given time to the external chemical agent, the more rapid will be its action. The chemist, in order to prepare a mineral for analysis, to decompose it or to increase the solubility of its elements, proceeds in the same way as the farmer deals with his fields. He spares no labour in order to reduce it to the finest powder. He separates the impalpable from the coarser parts by washing, and repeats his mechanical bruising and trituration, being assured his whole process will fail if he is inattentive to this essential and preliminary part of it. The influence which the increase of surface exercises upon the integration of rocks, and upon the chemical action of air and moisture, is strikingly illustrated upon a large scale in the operations pursued by the gold mines of Yaquil in Chile. These are described in a very interesting manner by Darwin. The rock containing the gold ore is pounded by mills into the finest powder. This is subjected to washing, which separates the lighter particles from the metallic. The gold sinks to the bottom, while a stream of water carries away the lighter, earthy parts into ponds, where it subsides to the bottom as mud. When this deposit has gradually filled up the pond, this mud is taken out and piled in heaps, and left exposed to the action of the atmosphere and moisture. The washing completely removes all the soluble part of the disintegrated rock. The insoluble part, moreover, cannot undergo any further change while it is covered with water, and so excluded from the influence of the atmosphere at the bottom of the pond. But, being exposed at once to the air and moisture, a powerful chemical action takes place in the whole mass, which becomes indicated by an efflorescence of salts covering the whole surface of the heaps in considerable quantity. After being exposed for 2 to 3 years, the mud is again subject to the same process of washing, and a considerable quantity of gold is obtained, this having been separated by the chemical process of decomposition in the mass. The exposure and washing of the same mud is repeated 6 or 7 times. and at every washing it furnishes a new quantity of gold, although its amount diminishes every time. Precisely similar is the chemical